Hi, welcome back. We're now in Chapter 3 of Kuchemann. Hooray! This is now getting into the flow physics, and both from the aerodynamics point of view and the engine heat addition point of view. So exciting stuff. Going to be a bunch of math. So I actually recorded 4 derivation videos before this. That there's some stuff in here that I even wanted to go work through myself to reconvince myself of some formulas, or some formulas that Kuchemann just drops that I didn't see, and I need to go do a whole bunch of math. So I'll highlight those. And in my very non-perfect handwriting, I've now drawn a box that we're going to examine fluid. Now there's going to be an airfoil inside of this box. And XYZ coordinates, X being streamwise, Y and then Z being the normal. And we're going to think about conservation of mass, conservation of momentum in this case. And ultimately, we know the force. I'm going to write it in kind of the Newton notation. So this is a vector, is kind of doing a contour integral, so going around all of these surfaces, and we're interested in P minus P0 and in that direction, right? This is the vector itself is on the surface normal. And then we have minus the contour of density, the velocity of the ith force we're carrying about, and then the jth surface. So the normal, like the velocity, basically this is the portion exiting that jth surface. I find this way more useful in this notation than just vectors, because then you have to remember what's being dotted with what and what's the free-floating vector. So this is my preference here. And just a reminder, I'm going to treat sort of this generic velocity vector, right? We would call it as u I hat plus v j hat plus w k hat. So XYZ components of this velocity vector. Okay, and so the lift would be the portion in the z direction. And the lift, if we then go through and see, well, what components does it have, especially in this kind of Cartesian system. Up front here, honestly, this was any blob I could have drawn. In this nice Cartesian system, we'll see that we only have a couple different forms of this. In fact, I better also write down that this is really generically, we're going to call this V0 plus U. What do I mean by that? That we have a generic flow coming into the x direction alone, and then we have a modification to that flow. That's actually how we're going to treat this. Okay? And so the lift component then would end up being sort of on negative A to A and negative B to B. Okay? And so that's kind of the front and side. And then we know that the flow coming in doesn't have any lift because it's just straight in the x direction. And so then this is simply on the exit plane here. You would have, and so since it's the lift direction, rho, the lift is z direction, so vi is actually just w. And then that the amount coming out the back plane is what's the velocity being dotted into that? That's v0 plus u into the back plane. Back plane is then just dy dz with those limits of integration. And just a reminder, this is actually at x equals, we'll call it infinity, this sort of back plane, infinity. So that's the portion on the front and back walls. Now we have to consider the portion on the sides and the top walls. Okay, and so you will also then have so I'm going to add into this generically the pressure term. Okay, the pressure is only going to change from bottom to top. Sorry, the pressure may change. The only pressure differences along the z direction would impact this. So this is P minus P0. And so this is integrating of minus B to B. And so that's across. And then we'll say minus infinity to plus infinity, basically the entire spectrum of the x distance. And so you have that component, that's the pressure term. And then you also pick up, because it's the bottom and top, the rho u, . So it's W again, because that hasn't changed. And the portion going up is W. So this is W squared. And then that is dy. And my dx will be on the other side of this. In fact, it's because I wanted this integral. I wanted the x integral separate. There we go. X integral separate. So that was the bottom wall, bottom and top wall, and now the side walls. And so the side walls are then just minus a to a, and it would be, again, it's still rho w. This part hasn't changed. I'm still talking about the lift. And so this time it's then the portion being carried out of the side wall, which would be any side velocity v, and then this is dz, and the whole thing then dx. Okay, so that's the lift component. And so we'll go through and simplify that here in a second, but I'm going to also now write down the drag component for this. Okay, so similarly, on the drag is now in the x direction. And so you would have any pressure differences, and then rho u, v plus u, kind of same sort of reason, right? The velocity component u, we already subtracted off the v0, and so you have the v plus u on the back side, and then that is dy dz, so that's the front and back plane. And then you have a minus, again, minus infinity to infinity. I'll get the square bracket in there, the right spot, minus b to b. And so you have the top and bottom planes, and so the portion affecting the drag, so this is rho u affecting the drag, and it's the part going out the top plane, so it's w, and then top plane is dya, the dx will be on the outside, and then a minus a to a, and then you have a rho, still rho u, that part didn't change, but then it's the stuff going out the side plane, dz. All right, dx. Okay, so that's the form. All we've done so far is going from this kind of contour integral into the form in this box. And so now we're going to talk about the characteristics coming out of this back plane. Okay, so namely on this back surface, I'm going to draw it up here. If we're looking in on this back surface, and there's we have a wing inside of there, and so we're actually capturing all of what's going on in that wing. That's why we're doing this, is we will see that there's sort of a vortex that's kind of caught in the plane. So the idea now is that saying this plane is far enough back, and A's and B's are chosen wide enough that you've captured the entirety of this thing, and it's so far back that basically these vortex loops are not, it is perpendicular to this back plane. So there's no extra forces happening here. It's kind of steady, which is not true in viscid, in Kuchemann. Sorry, it's not true in viscous. It would always be decaying if it's viscous. But this is so far an implicit approximation, and we're still going to learn a ton from this. And by the way, like when I said airfoil, normally if you've seen basic fluid mechanics, airlifting theory, you're going to actually start at this kind of 2D approximation and flow, Bernoulli's equation. That's all good and well, except we never build finite wings. So you're going to see here the power of sticking to all of this formulation. We're actually going to learn right off the bat what happens with finite wings. Okay, and so with this, we're going to have a couple, for sure, velocities. That didn't show up well enough. Let's see, stick to blue. Yeah, we'll stick to blue. So there is a downwash, and to be particular, we're going to put TR. It's the, I write it down somewhere there. The Ch3 plane. This stands for Ch3 plane. And that's the name of this procedure. So there's a downwash And there is also then theoretically a side wash that is on these planes. And if we have that information, we can now capture all of this. Okay? And so with this, we're then going to take a look at the terms, a couple terms that we're going to declare as small, namely this term, w squared. We're going to say that is close to 0. And VW, we're going to say is close to 0. Okay? For small things. And so then we can finish the lift equation. So WU, I think we're also ignoring, oh yeah, and also on this plane, we're saying U is equal to 0. Okay, that's any deficit has been fixed and turned into a downwash and side wash. All right. And so lift, if we go then through this, we get at the exit plane U is 0. So this is now, I'll leave the two integrations in there. Rho W V 0. And then you have still the dy dz. And then we've got the only thing that survives on this term, because that was 0, is the pressure term, okay? P minus P0. And we'll leave it there for just a second, and that's dy dx. And then we'll write down the drag. So same thing, double integral. And basically the only thing that survives in this drag term, because all of these were 0, so that's 0, right? Because again, this is at the exit plane. Right? That's 0, and that's 0. And so the only thing that survived is that pressure term. And so this is P minus P0, and then dy dz. Okay? So now we need to actually turn to Bernoulli. And from Bernoulli, we're going to get a relationship between P minus P0 for this term, right, on the lift side. And so going to Bernoulli, and this is a bit what I did in the other derivation. So if you need to see a little bit more details, you can there. But this is then just rho V naught U plus 1/2 in all of the variations squared. And pick up a 1/2 rho naught U naught squared Mach squared, right? So a Mach correction. And then also you have a rho over rho naught is equal to 1 minus U over V naught Mach naught squared. And so if you plug all those in, you will then see that P minus P naught is just equal to minus rho naught V naught times U naught times U. Okay, and this is at Z is equal to plus or minus A. So with that, we can come back and then show our lift. And so lift rho U, so let's pump out. So rho V naught, and then minus B to B. You still have this W minus W dz, and then a plus minus infinity to infinity of U, and then that plus or minus A dx dz, right? So remember, U is not U is 0 on the back plane, but it's definitely not 0 along the top and bottoms and sides. Okay, we could have some stuff going on. So, and this is then where using the potential flow is actually helpful, because then we can then say that W is simply the gradient of that potential in the Z direction, and that U is the gradient of the potential in the X direction. And then if you go through all that, you basically end up having that the lift, and I'm running out of space, so we'll kind of end it here. It's not an integral. Integral comes in a second. Rho u naught. Plug it in. You basically just get that this is the delta dy of delta phi. So the punchline is you can solve this, right? Because you go back to what we talked about, I think it was chapter 1 when we talked it through some of the velocity gradients. You can go solve this pretty easily. And so you actually know that it's just the change in delta. And where is that going to happen? It's basically going to happen, you can do that integration all around here, or you could just say, you know what, if I know the two differences, I'm actually done. So this is one of the reasons, again, potential theory isn't just useful in 2 dimensions. We actually are now fleshing it out. Kind of through all this math, we're able to flesh it out and come up with a lift term. And, you know, rather than driving all the drag one as well, I'll squeeze it in here so we can kind of be done and come back and talk through. Maybe I'll finish with one more thing. I got room here by my head. I can write one more thing. So you do the same thing with the drag term, and you end up having, this is 1/2 rho. Yeah, it's interesting. You got to convert all your different things. I'll just write it down as d phi dy. So it's basically, it was the side wash squared, and then d phi dz, that downwash squared. Okay, so you can solve for all of those things. All right, and so to have a little bit of a punchline, let me keep my head above water here, and I'll try to put my punchline right in here. Okay, so you can actually then figure out that if we just say that on this exit plane, again, this downwash is this Trefson velocity, you can actually write down the solution for the gradient of the velocity potential, and you can look in the book, but it's 2 times the span s, not the area s, times that velocity square root of 1 minus y over s squared. And so whatever that airfoil is, you know, sitting in here, whatever that airfoil is here and here, and you get your vortex shedding off of it, you can write down the velocity potential in terms of even the span-wise distance. And then you can actually finish this whole freaking integration. So you get lift is equal to pi over 2, and then you pick up your aspect ratio, which is awesome. That velocity over v0, that kind of the downwash velocity, where a is defined as its aspect ratio. So 4 times the span squared over area, and you know, that's a little less versus a big S. That's normally why I try to not keep the variables. Trying to keep as much as I can close to the textbook. And then what's neat is you then work through the drag. It's out of room. We'll just go to the punchline. You can do this same thing for the drag, and you get it's 1 over pi times aspect ratio lift squared. So with my head sort of barely poking over here all the equations, I'm going to foot stump on that and be like, look at this. We actually, through invested theory, showed how the drag scales with lift squared. This is a 3-dimensional effect. It is not a viscous effect. You know, we've talked about the vortices actually come off. As long as you're imposing the cutout condition, you have to impose a vortex in order to have the velocity come off evenly off of the leading edge. It's because of viscosity, but as long as you impose that velocity matching conditions, that first order effect of viscosity is just to provide the fact that you get these vortices. And then we can work this potential theory, carry through all the math, and we end up getting this very awesome result. And so already we have this insight that the drag is going to go like this, and that's why gliders would have a massive aspect ratio on their wings, right? That's the easiest way to have your drag go way down, is have these long, skinny wings. So, all right, we'll see you next time.